This is the opening lecture for Chapter 25, which covers current. Chapters 25 and 26 go together. Chapter 26, a continuation, is on simple circuits. All right, so let's begin with direct current. Okay, so let me begin by just drawing out a battery, like so. And then here's a wire, which connects to the other side of the battery. Here's high potential, here's low potential. Of course, now, as we've already described, the electrons would then flow through this circuit in a counterclockwise fashion. They would fall from low to high potential, like so. However, remember that electrons are negatively charged. It turns out that electrical engineers don't like to deal with negative signs. So because of that, what we then instead do is we ignore the negative sign, and we define instead what is referred to as the conventional current. Conventional current is labeled as I, and by definition, it flows in the opposite direction of the electrons that are actually flowing through the circuit. Instead, we define the conventional current, just so we don't have to deal with negative signs, as falling through the wire, if you will, from high to low potential. So the conventional current basically flows backwards of what actually happens, like so. Okay, now the mathematical definition of conventional current is as follows. Change in charge with respect to time. So it's how much charge is flowing past a certain point in the circuit per second. That's the easiest way of thinking of it. It's actually an example of a flux. Okay, now the units here of the conventional current are coulombs per second. A coulomb per second is given its own name. It's referred to as an ampere. As I just mentioned a moment ago, this is actually somewhat similar to a flux we've already seen. Recall a water current back from chapter 22 on Gauss's law. Okay, so recall the details of a water current. So a water current, we labeled it as the flux of water, was equal to the density of the water multiplied by the speed of the water as it passes by a certain point, and then multiplied by a cross-sectional area through which that water is flowing. Recall that the units of this quantity here was kilograms per second. So if you stand on the side of a river and you basically measure how much kilogram of mass passes you per second, you're measuring then basically the water equivalent of an electrical current. An electrical current instead is how many coulombs per second pass by your location. We refer to that as an ampere. Okay, now as the current passes through the circuit, it does not speed up in any manner. Think of the current as falling downhill, if you will, from high potential to low potential, but it does not speed up as it does. The reason for that has to do with a property associated with all electrical circuits, all matter for that matter, that is referred to as resistance. So as the actual electrons flow through a conducting wire, they basically interact with the atoms that are present within the wire. This then converts some of the kinetic energy associated with the electrons into heat, and this basically ensures that more or less the current travels through the wire at essentially a constant speed. That constant speed is actually quite small, and it's referred to as the drift velocity. The water equivalent of this would be, imagine doing the following. Take a piece of paper, place it into a current of water, and then it flows downstream. Okay, measure the distance that it travels, measure the time that it travels, and then therefore the speed is just distance divided by time. Same exact thing here with respect to the electrical current. Imagine watching the current pass by your location, you measure it, travel some distance, you divide by the time necessary for that to happen, you've measured what is called the drift velocity. Now getting back to the water current, the actual individual water molecules themselves are moving at a much greater speed than the overall drift velocity of the water current. Same thing here with the individual electrons. The individual electrons, as they basically fall downhill here, are moving at speeds that are in the neighborhood of about 1 billion times greater than the drift velocity itself. Now, 1 billion times greater sounds like a lot, the individual speeds of the individual electrons themselves are usually in the neighborhood of a few tens of kilometers per second. So basically, the overall drift velocity of the electrical current itself is about 1 billion times less than that. So we're not talking about basically the motion here of the individual electrons. We're talking about the motion of the current itself. The current itself is actually moving quite slowly. Here's a nice analogy to use that we can then use to describe resistance. Imagine, for example, a pinball machine. Okay, and then right here is the pinball machine like so, if you were looking down upon it. Let's say that this right here is high potential, so it's at a greater height, and this right here is low potential, so it's at a lesser height. This is high potential, we'll say this is low potential. And then you have individual pinballs, for example, in the pinball machine. And of course, these pinballs are rolling downhill, like so. Now, if there was nothing in the pinball machine except for the balls themselves, then the balls, of course, would accelerate as they roll downhill. What then prevents the individual pinballs from speeding up more or less as they roll downhill? Well, imagine now bumpers in the pinball machine. So I'm going to put some bumpers in like so, as these red circles. And then as the pinballs themselves collide with these bumpers, this then slows down the pinballs, of course, and it also converts some of their energy into heat. The exact same thing is happening when electrons are passing through a wire. So imagine that these are the electrons themselves, and these are the atoms that make up the wire. As the electrons fall downhill, if you will, in this case from high to low potential, like so, we're ignoring the negative sign here of the electrons. Well, normally they would speed up as they do, but they don't, and the reason why is because they interact with the atoms of the wire itself. This then converts some of the energy into heat, and this property is then referred to as resistance. So as the conventional current flows through the wire, it essentially does so at a constant speed. That's called the drift velocity. Once again, picture the analogy with water with a piece of paper, for example, and we're not necessarily talking about the individual speeds of the individual electrons themselves. Okay, we'll get to those details a little bit later on in the chapter. Okay. Okay, let me do some erasing here. Okay, now there's a specific way in which we draw out the symbol associated with resistance. That's the following. So once again, here's the battery, voltage V, high potential, low potential. And then we represent the overall resistance of the wire itself as this jagged symbol right here, and this is the resistor symbol, the resistance R. Okay, now as the conventional current flows here from high to low potential, like so, we always picture the straight lines themselves still as equipotential surfaces, just as we did, for example, earlier when talking about electrostatic situations involving capacitance. However, we just draw then the overall resistance of the wire itself as a small symbol like so. It's important to realize that the entire wire is a resistor, but we don't draw a jagged symbol to represent the entire wire. We instead just draw this simple symbol like so. And then right here would be high potential, right here would be low potential, and the conventional current falls downhill. There's a very simple relationship between current, voltage, and resistance for most simple metals that we use in electrical circuits, primarily copper, tungsten, aluminum, and a few others. This simple relationship between the three is referred to as Ohm's Law. Okay, Ohm's Law is an empirical property of these metals. Empirical property of metals commonly used in electrical circuits. That is copper, aluminum, tungsten, and a few others. Ohm's law is essentially described in the following way. Let me plot the following graph. Okay, let's plot conventional current I here as a function of the voltage V. Okay, as you increase the voltage V associated with the circuit, it's like increasing, if you will, the tilt of the hill or the size of the hill, then therefore the conventional current is, of course, going to increase. Okay, it does so linearly for these types of metals, like so. It's a linear progression. So once again, current as a function of voltage. If you increase the voltage of the circuit, you then therefore increase the current. It does so linearly for these types of metals. Okay, we write this then in the following way. I is proportional to V, and then the proportionality here that I'm going to write, such that this is an equal sign, now takes into account this property of resistance. That's written in the following way. Like so, where R is the resistance itself. Okay, basically think of the expression in the following way. For a particular voltage, if you increase the resistance, it's like putting more bumpers in the pinball machine, if you will, then therefore the value of the conventional current decreases. Okay, let's say that you decrease the resistance, so it's like you have less bumpers in the pinball machine, so then therefore if R is a small number, that then means that the current is going to be a large number. Once again, metals that have this property follow what is called Ohm's law. Sometimes we refer to these metals, by the way, as ohmic. Okay, more commonly we write the expression Ohm's law, however, in the following way. We usually move the resistance symbol to the other side, and we write Ohm's law in the following manner. Okay? Okay, the units associated with resistance, once again, it essentially just comes out of this graph here. The units of resistance are going to be in terms of volts per ampere. A volts per ampere, however, is given its own name. It's referred to very simply as an ohm. So the units are volts per ampere, which is referred to as an ohm. We actually use the symbol, the capital letter omega, to describe an ohm. That's written like this. Okay. Okay, now exactly how much energy is being delivered here by the battery as the conventional current flows through a circuit. And once again, we just have a resistance R associated with the wire. Let's take a look at that next. We actually do this as a power calculation. Okay, so now what we do is we take a look at the power delivered by the battery. P deliver, as this is referred to as. Okay, the power delivered by the battery is nothing more than the change in the battery's chemical potential energy per time. Like so. And the change in the potential energy of the battery is equal to the infinitesimal amount of charge that is flowing per time, multiplied then by the voltage V. Like so. So recall, of course, when talking about chapter 23 for potential, electric potential that is, remember that potential energy per charge is equal to potential. So then therefore the potential energy can be written then as voltage multiplied by charge, like so. Okay, now this right here, of course, is the current I. So then therefore the amount of power that's delivered by a battery is equal to the conventional current I multiplied then by the voltage V. Okay, now if all that we consist of here in this circuit is a resistor and nothing more, then this quantity here is also equal to the amount of energy per second that is being lost as heat as the conventional current passes through the wire. This right here is equal to what is called P loss if the circuit only consists of a resistor. A resistor with resistance R. So then therefore across the resistor itself, let me just focus on the resistor Okay, and then we have the conventional current I flowing from high to low potential. Right here is the resistance, the resistor of resistance R. And then the potential here across the resistor is the same thing as the potential across the battery. Once again, this is assuming that there is nothing else in the wire except the wire itself. There's nothing else in the circuit there, that is, except for the wire, which we just consider to be a single resistor. Okay, here's then how we can write the amount of energy lost as heat per second as the current flows through the resistor. Okay, now I'm going to go ahead and use P deliver here because ultimately these two quantities are the same if the circuit only consists of a resistor. The V here, it's important to understand, is not just the voltage of the battery, it's the potential difference here across the resistor itself. So then therefore I can write this expression here a couple of different ways by using Ohm's law. Replace the V, for example, with I times R, and if you do, you end up with this expression here. Or replace the I here from Ohm's law as V over R, which then gives you this expression here. So this quantity here is always the power that is delivered by the battery itself. These guys here and here, however, are the amount of energy per second that is being lost as heat through the resistor itself. If there is nothing else in the circuit except for the wire, then these quantities are all equal to each other. Okay? Okay, I'm going to go ahead and pause the video here. That concludes part 1. I'll just get to part 2 in just a few minutes.